Well, hello and welcome to Doc Ontko Physics. Keith Ontko here. Today what we want to do is we want to go over the second part of our magnetism lesson. So this is magnetism lesson part 2. And what we want to do is we want to look at the forces that are on current carrying wires and the interactions between current and magnetism. And so the first thing we want to look at is the force on an electric charge moving in a magnetic field. And so many of you are probably not familiar with the old style television sets, but the old style TV sets, or even an old style computer monitor, they had things in there called cathode ray tubes. And what a cathode ray tube was a tube that fired out a beam of electrons. And that beam of electrons would go through two fields. It would get affected by an electric field, and it is also controlled by a magnetic field. And so what we want to look at today is we want to look at and see how a charge, an electric charge or an electron, is affected when moving through a magnetic field. And so we've seen that if we have, let's switch to pencil there, there we go. If we have a wire and that wire has a current in it, then we have a magnetic field that surrounds that current. Well, what is a current made up of? Well, a current is made up of individual electrons. And so we can think of this in the same way. What happens when one electron moves through a magnetic field? And you can see it in the picture down in the lower right-hand corner. We can see the diagram of an electron. That would be the tiny little blue dot there. And let me see if I can just slide this down a little bit here. Oops, I got rid of too much there. That's okay. So we have an electron here. We have a proton here, or a positive charge there. And they are going through the magnetic field. And one thing that you may notice very clearly is that when the electron goes through the magnetic field, it feels the magnetic field, but what is the direction of the force on that electron? Well, it flies up to the top. What's the force on the positive charge? Well, it flies down towards the bottom. So they each feel a force, but the direction of that force is different. For one, it's going to be going up. For the other one, it's going to be going down. And again, we can figure all that out with a thing called a right-hand rule. And so we're going to use the right-hand rule again, except this time we're not going to be using the right-hand rule for a magnetic field going that's traveling, moving around a straight current-carrying wire, which we see on the left-hand side of the screen. Right? That was I point my thumb in the direction of the current, and the magnetic field follows the curvature of my fingers as they curve around. In this case, we have another right-hand rule. And in the papers that you'll see that I've posted on the internet, this should be right-hand rule number 3, right? And this is the right-hand rule where my fingertips are going to point in the direction of either the current or the charge. Because remember, a charge is just a tiny electric current. So my fingertips will point in the direction of the current or the charge, whatever that direction is. The magnetic field will point in the direction, or my palm will point in the direction of the magnetic field. Okay, so fingertips go in the direction of the charge, the velocity of the charge. Palm points in the direction of the magnetic field, all right? And that leaves my thumb. My thumb is going to point in the direction of the force on that charge. Now, important thing, the right-hand rule is for a positive charge, all right, or we consider a positive current, all right? If I want to know what the force is for a negative charge or an electron, I do the same thing, all right? I do the right-hand rule, direction of the current with my fingertips. My palm points in the direction of the magnetic field. My thumb is going to point in the direction of the force. But now because the charge is negative, it's an electron, whatever value I get for the direction I get for the pointing of my thumb, I'm just going to flip it. So if it was up, it's going to be down. All right. So let's take the picture on the screen here what we have is, and let's take the proton, or positive charge. So the positive charge is going into the board, okay? So I'm going to point my fingertips into the board. The magnetic field is pointing to the right, so I'm going to have to take my hand and I'm going to have to twist it to the right, all right, while leaving my fingertips pointing in the proper direction. And then my thumb is now forced to point down. And what's the direction in the picture that the positive charge is going? It's moving in the downward direction because the force on it is down. Okay, so that's the right-hand rule for the force on a charge in a magnetic field. Okay, now since this is physics, we not only have the direction of the charge, but we have the value of the charge, right? Since we have a direction, we have a value. That means the force, the magnetic force on this charge is going to be a vector, right? And the equation for this is Q times V times B times the sine of theta. What's Q? Well, hopefully we all remember what Q is. Q is just the value of the charge. What's V? V is the velocity of the charge in this case, right? And what is B? B is the strength of the magnetic field in Tesla. So Q times V times B times the sine of theta, okay? And so what we need to do is look at the angle between the velocity of the charge and the magnetic field. In this case, they're perpendicular. So the sine of 90 degrees is just 1, and the sine 90 just turns into 1. We don't have to pay much attention to it. In many of the problems that we're going to do, that's the case. The velocity or the direction of the current is perpendicular to the magnetic field. And so the force just ends up being Q times V times B. All right, so let's do an example. Say I want to find the magnetic force on a proton that is traveling through a magnetic field, and the magnetic field is the Earth's magnetic field. And so the proton is moving with a velocity of 1 times 10 to the 5th meters per second. It's moving through the Earth's magnetic field, which is typically about 55 times 10 to the minus 6 Tesla, or 55 microtesla. And when the proton moves eastward, the magnetic force is at a maximum. When it moves northward, no magnetic force acts upon it. So we want to know when it is moving eastward, what's the magnetic force? And so it's at a maximum, so the sine of 90 degrees is 1, right? All right, because the sine of any angle, the maximum it can be is 1. So FB is just going to be QVB times 1. So Q is the charge on a proton, 1.6 times 10 to the minus 19th coulombs, times the velocity of that charge, 1 times 10 to the 5th meters per second, times the value of the magnetic field that is traveling through, which is 55 times 10 to the minus 6 Tesla. We multiply these all together, and the force on our charge is going to be 8.8 times 10 to the minus 19th newtons. Now, what if we wanted to know what the acceleration was on our little proton? Could we find that? Absolutely. Well, the mass of a proton is 1.67, whoops, that's not a good 6, times 10 to the minus 27th kilograms. All right. We know that our force is 8.8 times 10 to the minus 19th newtons. So we can just use Newton's second law, sum of the forces equals mass times acceleration, to get the acceleration. So 8.8 times 10 to the minus 19th newtons divided, oops, that's not, it looks like a Christmas tree, divided by 1.67 times 10 to the minus 27th kilograms will equal our acceleration. And when we do that math, we get, so the acceleration would be about 5.27 times 10 to the 8th meters per second. Now, it would not be able to accelerate at that velocity for very long because we would break the speed, the greatest speed that anything can have, which is 3 times 10 to the 8th meters per second, and that would be light. So it could only accelerate at that speed for a tiny fraction of a second. Okay. So that's an example of the force on a positive charge, a proton, moving through a magnetic field. So now again, I just want to go over the right-hand rule again, all right? The right-hand rule there's a picture on the page here that shows one version of a right-hand rule. I don't love this one. There are many different ones. The one that I use is all of my fingers point in the direction of the current or the charge. My palm points in the direction of the magnetic field, and my thumb will point in the direction of the force. So don't pay no attention to the picture on the screen there. I don't really like that one, although it's perfectly valid if you want to use that one, but I like to use the one that I just told you about. Now, one thing that is important though is, when we're doing problems that have to do with charges and magnetic fields, we're talking about things at 90 degrees, or at angles anyway. So we're talking about three-dimensional types of problems. And so, for example, I can have a current going up and down, right, on a page, but a magnetic field going in and out of the page. Or I can have a magnetic field going up and down the page and the current moving in and out of the page. So how do we actually show that on a piece of paper? Well, the best way to do that, and the convention that's used is, if we look at this diagram right over here, a circle with a dot means that whatever that thing is, whether it's a magnetic field or a current, is coming out of the page. And the best way to think about it is an arrow, right? So here's an arrow. I'll try to draw it the best I can. All right. That's not a great arrow, but it's not bad. All right, so I've drawn an arrow on the left-hand side of the screen. If you had an arrow coming at you, what would you see? Well, you would see the point of the arrow, which is exactly what you see if the thing is coming out of the page. All right, so if the arrow is coming at you, you would see a dot. All right, if the magnetic field, for example, is coming out of the page at you, it's going to be depicted with a dot. If it's going into the page, right, it's going to be a circle with an X in it. Okay, well, what do you see if an arrow is moving away from you? Well, you see all the little feathery things at the end there, right? And usually there's 4 different feathers. I can only draw 2 of them on there. And what do you see? You basically see a cross, and those are the feathers at the end of the arrow. All right. So that's the convention that we use for things going into a page, things coming out of a page. And again, right-hand rule. There's two different ways you can remember this. One is look at the piece of paper that I've included in the lesson. Right, I've got a piece of paper there with the right-hand rules. There's 3 of them. This is the third one. Again, fingertips point in the direction of either the current or the electric charge that's moving. My palm points in the direction of the magnetic field, and that will leave my thumb, and that will always point in the direction of the force. This is for a positive charge. What do we do for a negative charge? We take whatever answer we get and flip it upside down. Okay, so that's the conventions there. All right, so let's look at a couple of different examples of using the right-hand rule with problems that you could typically see on a piece of paper. Okay, there's 3 examples here. I'm going to circle all 3 of them so you don't get confused as to which one. There's this one. There is this one. And there is this one. These are the 3 examples. This diagram over here is just showing you that a positive y goes up, positive x goes to the right, and positive z is coming out towards you. Okay, so that's a 3-dimensional system. So let's look at this one first, right? And what we have is we have the velocity of a particle that is moving in the upward direction. We'll make sure we believe it's a positive particle. So the velocity of the particle, right, because the v is right next to that line moving upwards on the page. So my fingertips are going to point up, all right? The magnetic field, which is given by the letter B, capital B, is pointing to the left on my page. So I'm going to point my palm to the left. And my thumb, therefore, is forced to point out of the page at me. Okay? And so what's the direction of the force? The direction of the force is in the positive z direction. It's going to be coming out of the page, right? And I would depict it like that. Okay, that would be the force in this case. We're given the velocity, we're given the magnetic field. We can get the direction of the force. All right, let's look at this example. Example number 2 over here on the lower left. What we're given here is, again, we're given the velocity. In this case, the velocity is going from left to right. All right, we have that vector. We have a magnetic field now that's coming out of the page. It's a circle with a dot. All right, I want to know the direction of the force again. Well, this is going to be a little tougher because I'm going to have to take my hand and move it in strange positions. But I'm going to take my hand, and my fingertips are going to point to the right. Right? I'm going to now have to twist my hand and point my palm out of the page. Right? And where does that leave my thumb? My thumb is now pointing down in the negative y direction, and that's exactly what we have right here. Right? The force is in the negative y direction. Right? Let's do one more. Let's do number 3 over here on the lower right-hand side. All right? Velocity is going up. This will be easier on my hand. All right, so the velocity is going in the up direction. The magnetic field is going into the page in this case. All right, and so this will be, we want to find out the direction of the force again. Well, let's see. Velocity is going up, so my fingertips are pointing up. The direction of the magnetic field is into the page, so my palm points into the page. And what's the direction of my thumb? It is pointing to the left or in the negative x direction. Okay, so we have a force in the negative x direction. All right, so that's how we use the right-hand rule number 3, to figure out directions of forces and things if we have a charge or a current that is in a magnetic field. Okay, so let's do a couple more examples. All right, and in these cases, we're not necessarily just looking for the force. We could be looking for the force in the top example. We'll be looking for force. In the lower left example, we're going to be looking for the magnetic field direction. In the lower right over here, we're going to be looking for the direction of the velocity. Going to do the exact same thing. Right? So for the top one, let's see. I'm going to take my fingertips. I'm going to point them in the direction of the velocity, so they're going up. But now I've got to twist my my fingers to point in the direction of the magnetic field that's going to the right. And therefore my thumb is going to be pointing into the page. Okay. Now, remember that this is for an electron, right? Up here, and I've neglected to say that. This is for an electron. It's not for a positive charge. So, again, fingertips going up, magnetic field going to the right. My thumb is pointing into the page, but what do we do for a negative charge? We flip whatever answer we get. And so instead of the force going into the page, it's coming out of the page in the positive z direction. Okay? So whatever answer you get, the normal answer you get using the right-hand rule, you just reverse that for a negative charge. All right, so let's do problem number 2 on the lower left over here. All right. What do we got? Well, we have a velocity, looks like that's going to the left, and a force on the charge that looks like it's going in the positive y direction. In fact, it states that. So the velocity is going in the negative x direction. The force is going in the positive y direction. We want to know the direction of the magnetic field. And again, this is on an electron. So let's take my right-hand rule. All right, my velocity is going to be going in that direction. So I do this. The force is going up, right? So I still have my fingers pointed to the left, my thumb is pointing up, and my palm is pointing towards me or out of the page, right? But remember, this is an electron, and so the answer I'm getting is out of the page, but I've got to flip that answer, so it's going to be going into the page, and that's exactly what we have here. B is negative z, or it would be going into the page like that. Okay. Let's look at our third example over on the lower right-hand side over here. This time we have a magnetic field coming out of the page, right? The circle with the dot. We have a force going up, and we want to know what the direction of the velocity is on our negative charge. Well, let's see. Force is going up, magnetic field coming out of the page, and so my fingertips are pointing to the left, all right? Force going up, magnetic field coming out of the page, fingertips to the left, but I've got to reverse that, and so it would be fingertips to the right because it's an electron, and the velocity is plus x, or to the right. Okay. All right, so again, we've had two examples of using the right-hand rule, one with a positive charge, one with a negative charge. And these right-hand rules work the exact same way with an electric current. All right? So just because it's an electric current, that's no different than an electric charge, except there's a lot of electric charges. And you use the right-hand rule in the same exact way, except the fingertips, instead of being for one charge, it would be for many charges in the charge of the current. Okay. All right. Okay, so what if we have an electron and it's shot into a very large magnetic field? So make believe the entire page here is a magnetic field, and it looks like it's going into the board because it's got X's, right? So we have an electron here being shot into a magnetic field that's over here, and we're going to make believe it's much larger, okay? And what's going to happen to this electron when it hits the magnetic field, as long as the magnetic field is large enough? What's the path going to look like once this electron gets into this magnetic field? Well, all we really need to do is take the right-hand rule and see if we can figure that out. All right, so again, I'm going to take my hand. I'm going to have to, rearrange my hand a little bit here. So my fingertips point in the direction of the velocity, okay? And this is really going to be tough. My palm points in, it's going to point into the page. So fingertips point in the direction of the velocity. Palm is pointing in the direction of the magnetic field, which in this case is into the page. And the force is pointing up, but remember this is an electron, so the force is actually going to be going down. So when the electron hits the magnetic field and is at this position right over here, right? Actually sooner than that, but it's going to feel a force going in the downward position. Okay, so what's that going to cause the electron to do? What's going to cause the velocity of that electron to change, right, and change its direction, right? Think about an object, right, at the end of a string here that is moving in a circular path. Okay, this object has some tangential velocity, and what's the only thing keeping that object in a circular path? Some inward force, right? The force is always going to be inward, okay? Well, think about the electron going in this magnetic field. Hits this magnetic field, what's the force it feels? It feels a downward force like that, towards the center of some position. Now let's say the electron changes its velocity, gets to this point right over here. Well, what is the force that it feels now? Well, the electron is now traveling, say, in the downward position. So fingertips pointing down, okay? The magnetic field is still pointing into the page, so I got to turn my hand like this. And what is the direction of my thumb? Well, it's pointing to my right, but because this is an electron, it's going to be to the left. So what's the direction? It is pointing inward, all right, towards the center of a circle. And so what's going to happen is if we take all of the individual right-hand rules for all of the different positions of the electron, right, what's going to happen is the path of this electron as it goes into this magnetic field is going to be a circular path, right? So if the magnetic field is a small magnetic field, right, it's probably not going to be able to go in an entire circle, but it will go in a curved path as it's going through that magnetic field, right? So if it's a small magnetic field, if this was my electron and this was, say, my magnetic field over here, when it hits this thing, it's going to hit it, start curving, right? And now once it leaves the magnetic field, it will continue going straight. So it curves while it's in the magnetic field, right, in this area right in here. Once it leaves the magnetic field, it's just going to continue going in a straight path, just as our object at the end of a string would go on a straight path if it lost that centripetal force. Remember, if the string breaks, what happens to the path? It's just going to be straight. All right. So either a negative charge or a positive charge traveling in a magnetic field will go in a circular path. If a negative charge goes in a path that's like this, it's going downwards, Guess what the path is going to look like for a positive charge going into a magnetic field that's going into the page? Well, it's going to look like that. Right? It's going to go upwards. All right? So you simply use the right-hand rule in each case to figure it out. So as I just mentioned, an electron or a proton, or a negative charge and a positive charge, entering some kind of a magnetic field is going to move in a circular path, right? Either an entire circular path or some portion of a circular path. What did we say back when we did circular motion? Anything moving in a circular path has to obey this equation up here, right? Right? If it's moving in a circular path, it has some centripetal force forcing it to move in that centripetal path. So the centripetal force is mv squared divided by r. And then in the back when we did centripetal forces, we listed a whole bunch of, or 3 or 4 anyway, of forces that could cause that object to go in a centripetal path. It could have been gravity, right? It could have been the tension of a string. It could have been friction. So we covered all those. And I remember saying that there's also other forces. There's an electric force. There's also a magnetic force that will cause an object to go in a circular path. Well, what's the magnetic force in this case? Well, it's Q times V times B. All right? And so if the magnetic force is QVB, that's the force causing it to go in a circular path, and Fc is mv squared divided by r, well, then we have this nice equality here that QVB is equal to mv squared divided by r for a charge moving in a magnetic field. Okay, that charge is moving in a magnetic field. It's going to take on a circular path, and so we have the equality that QVB will equal mv squared divided by r. Okay, and so let's do a couple of examples like that. Okay, so here's an example, and everything's not going to fit on the page, so I'm going to have to slide it down a little bit. But we have a singly charged positive ion with a mass of, let's switch back to pencil here, a mass of 2.5 times 10 to the minus 26 kilograms, so it's pretty small. And it's accelerated through a potential difference of 250 volts, okay? And the ion enters a magnetic field of 0.5 Tesla in a direction perpendicular to the field. All right, so the sine of theta is going to be 1. We want to figure out what the radius of the path of the ion in the field is going to be. Okay, so well, what do we know? We know the charge on this positive ion, right, is going to be 1.6 times 10 to the minus 19th coulombs, because it's just a positive ion. Right? We know the mass of it. Right? We know the voltage of the potential difference is 250 volts. We know the magnetic field is 0.5 Tesla. We would like to know R. Okay, so do we know everything that we need? Well, it's going to go in a circular path. We're looking for R. So ultimately, right, we're going to use this equation here. Well, what do we know? All right. Well, we know B, and we know Q. All right, we're looking for R, all right, we also know M, all right, we're told the mass. We do not have the velocity, all right, so we need to figure out what the velocity is. Well, if you remember back from our electric potential days, which isn't that long ago, all right, we have this equation down here that the voltage, all right, or the electric potential is equal to the work divided by the charge. Work on a charge divided by the charge. Well, the work on a charge can also be kinetic energy of that charge, because work and kinetic energy and potential energy all one and the same basically, and which is 1/2 mv squared divided by q. Okay, so we can take that information and we can figure out what the velocity is. I'm going to have to scroll the screen down a little bit here, since it wouldn't all fit on the screen. So we can figure out the velocity here simply by plugging in the values. So the velocity, we rearrange this equation up here to solve for V. V is equal to 2 times the voltage times Q divided by M. We plug in the values and we get a velocity of 56,568 meters per second. We now know the velocity, so we have V, right? And obviously V squared. We know everything we need to plug in, to substitute in and solve for R. R, when we plug all the values in, turns out to be 0.0177 meters. All right, so that's the radius of the curvature of the positive charge moving in some magnetic field would be roughly 1.7 centimeters, or 0.0177 meters. All right, so it's going to move in a circular field, right? And it's going to have some radius. We can use this equation to get there. This problem made you think a little bit more because it didn't give you the velocity, but it did give you the voltage. Be careful of the V's, right? Voltage is a capital V, velocity is a little v. So don't make the mistake of saying, oh, we have a V of 250 volts and just try plugging that in here. That's not going to work. All right, you're going to get a wrong answer there. So be careful there. Okay, so up to this point we talked about single charges moving through a magnetic field, but I've also mentioned that a current running through a wire is just made up of many particles or charges, right? Many electric charges. So it's really no different. So if I have a stream of electrons moving through, that are in a wire moving through a magnetic field, those electrons collectively are going to feel a magnetic force, right? So remember, FB equals Q VB sine theta, right? And so collectively, all of these electrons in the wire, the current carrying wire, are also going to feel a force, right? So let's take a look at what that would be. And so what we have here is we have our equation, all right, FB equals Q VB, all right, and we're going to assume that the sine of theta is just 1, okay? Well, what is velocity? Well, velocity is displacement divided by time, all right? So we can change this as Q times meters per second, all right, times B. Well, what is current? Current, I, is equal to charge, Q, per second, right? That's just I. Well, what do we have over here? Well, we have Q per second, right? If instead of having this S under the M, well, what if I put it under the Q instead? That's perfectly valid, all right? So that now I'm left with FB equals Q times meters times the magnetic field. Well, meters isn't the proper unit to put in there, but meters are usually given in length, right? So the magnetic field, the magnetic force is equal to, this shouldn't be Q, this should be I, I'm sorry. I times M times B, or I times L, the length, right, because meters are given in length, times B, and we can add in the sine theta over here. So this equation here, the magnetic force on a current carrying wire, is really the same as this equation up here, QVB sine theta. All right, it's just rearranged for many charges running through a wire, so it's ILB times the sine of theta. So the force on a current carrying wire in a magnetic field is I, the current, times L, the length of the wire that's actually in the magnetic field. So it can't be the entire length of a wire if only a portion of it's in the magnetic field. It's just that portion that's in the magnetic field, times B, the strength of the magnetic field. Using the right-hand rule, can we figure out what the direction of that force is going to be? Yeah. Let's take a look at the problem in the lower right-hand side here. Current is pointing to the right, and we always use a positive current. So my fingertips are going to point to the right. The magnetic field is pointing into the board, the little yellow X's there on the bottom of the paper. And so my thumb, hopefully you can see this, is pointing up. So what's the direction of on the wire going to be? It's going to be in an upward position. And remember that even though we have electrons running through the wire, we always use positive current flow. And so the current that's moving to the right, we consider that to be a positive current flow. It's just a convention, right? So if the current is moving to the right, right, that's positive current flow. My palm is pointing into the board or into the page, thumb is pointing up. So the force on the wire is going to be in the upward direction. This is very interesting because this is what makes a motor work. All right, if you've ever taken apart an electric motor, it's just a bunch of wire wrapped around a spindle that is sitting between two magnets. And when current runs through that wire, that motor, right, starts to turn, right? And that's what makes a motor, right? Just current running through a wire. Okay, so this ends magnetic fields and forces lesson part 2. We're going to continue this with magnetic fields and forces part 3. We're going to continue with currents running through a wire and actually what makes, why there's a reason for there to be a magnetic force on a current carrying wire. What's the real reason behind that? And we'll talk about that in part 3. So I hope this helps you. Again, we have magnetic fields and forces lesson part 1. This is part 2. And stay tuned for part 3.